these gentlemen. Oh, okay. It's oh shoot! I just let somebody in, and I did not get to see who it was. I found give me just a moment to save my attendance so I don't lose my work. Because what happens, and it keeps happening. I was just about to say that every time I click save and I get ready to start the lecture, somebody else trickles in. It's really funny, but it's fine. Just give me a moment. Because my goal is to like go through everything once. You know what I mean? So. Yeah. So welcome scholars. Let me just get back here. So let's see. So I'll check attendance again. So I'll check attendance again. I usually check it about 15-minute mark. So that's in about 10 minutes. So if students come in, they just got to be patient because I don't want to give up and do so much back and forth. Let's see. So this is what the top of, I don't even know what week it is. I'm like totally losing track of everything. Let's see. Give me just a moment. Let me pull up my syllabus here. Let's pull up the syllabus really quickly. Actually, no. It is week 6. Okay. Yeah. So for you all, this is the top of week 6, right? Yeah, because my other students are taking their exams, right? So we're here at the top of week 6. We're continuing chapter 3. So we had our exam 1 that was over the first 3 sections, right? Our rhythm is pretty much 1 section per week, right? And today we're going to do something a little bit different. Also, don't be surprised if one day or a couple of days to get your attendance credit, I might have you showcase some question, just walk me through a question or two to get your attendance credit. So I'll probably do like one-on-one sessions, either you can describe it to me or your screen, like if you're working on an iPad or something like that, and you feel, or you can like, if you have a video, you make it into like a projector or something like that. Just if I do that a day or two, don't be surprised. But that's for like attendance credit for that day. I might do it a couple of times. I just want to get some feedback from you all. But I think there's a whiteboard option on here. I just want you to showcase like, like I might pull up something that you submitted and then say, hey, walk me through this, right? And so that would be, right now I don't want to do it for more than the attendance credit. The original thought was for it to be like a oral quiz or exam, but I don't really want to do all that. I'm totally being lazy, but I want to engage with each one of you guys and just get a feel for where you're at. Each person is at. Okay, but just don't be surprised if I do that at some point. So again, in the spirit of procrastination and being lazy and just being human, right? Usually I like to get you guys lectures loaded up early. I was not able to do that. So what I'm going to do today is I'm going to go ahead and start the lecture. The lectures that I usually do early, I'm just going to do it now. And then, I'll keep an eye on the clock and I'll say, hey guys, okay, class is officially over. If I'm not done with the lecture, I'll release you guys, but I'm going to keep going until I get one complete presentation on the lecture, right? I kind of glanced at these in advance a little bit, but usually I don't I don't really work stuff in advance. I just load it up and start working right there on the spot. And what you see me doing, if you ever watch my recorded lectures, that's usually just me open it up and just start talking. That's it. Like, I don't really do any prep. I've done enough preparation through the years. Like, I don't prepare for any of this stuff. And I do that intentionally because, and I kind of talk out loud to give a glimpse into some of the logic and at least the way that I'm thinking, right? A lot of this experience is not really about the correct answer, which is obviously important, but it's more so about why is that the correct answer, right? That's just mathematics. This isn't like an abstract thing or anything like where it's open to interpretation. Not this. This is more concrete. It's either right or wrong, black or white, you know. But a lot of this is like about pattern recognition and knowing why is it there. So it's not, is that the correct answer? Is why is that the correct answer? So, okay. So let's get started with this. So we're continuing chapter 3 with exponential and log functions. Oh, and also just feel free to unmute yourself just to stop me and get my attention if you have questions, comments, or concerns. Also, don't hesitate to email me. I know I don't really respond to those because I just be in my own world. Again, if I don't respond before we meet, just ask me during class, right? Because again, the real intent is for this to be a study session or a Q&A. But I just fill it with different presentations because, you know, I understand if you guys don't want to talk. But again, another thing is whoever does the most talking does the most learning. If I'm doing all the talking, I'm doing all the learning. But again, you know, another reason that I run my class the way that I do, as far as I'm concerned, at this stage in your all's life, you're an adult, right? So what that means is like, if you don't want to take this serious and you want to do it however you feel like you need to do it, hey, that's on you. You're an adult. My job is to make the information available, be available, answer questions, and then, you know, the rest of it, you know, you're an adult, right? So whatever path you choose to walk, we just walk that path together and we just work it out, right? But I treat you all like adults. Like if we were in person, that's what I would have said to you the first day. And that's generally how I run it. I put the responsibility on you because at some point in your life, you have to start being accountable for yourself, right? So then the choices that you make and your choices and your actions directly influence your experience, right? The same, we all succumb to this. I have to, my experience is a direct result of my choices and actions. And so I don't have nobody to blame if my stuff goes left, but also I get the glory if my stuff goes right or whatever, you know? So that's just philosophy, just a little bit of insight into why I run my class the way I do, and just, you know, so that you guys, like, I just don't want you to get caught sleeping. You know what I mean? I don't want nobody to be set up for like failure. I want you guys to be set up for success. Okay. I love that this is recorded too, because sometimes I share things and if you ask me again later to regurgitate it, I can't repeat it. It was in the moment. So anyway, okay. So moving along. So we're looking at chapter 3. We're continuing chapter 3, exponential and log functions. Let me see. Another thing, so if this is week 6, I think your exam 2 is during week 8, right? And that's going to be over chapter 3. And then right after that week, we're going to start spring break, right? Hopefully we did not run. You probably wouldn't even recognize me if we ran into each other in the real world. Sometimes I'll be out and I've run into students. And I've been like all over the world. People are like, dang, how are you here? But yeah, so we got 2 more sections in this chapter. And then again, exam 2 is going to be over all of chapter 3, right? So I know 3.1 will be kind of tested twice, but you can't do the later sections in chapter 3 without doing section 3.1. So, okay. So then here, we're looking at section 3.3, rules of logarithms. So some objectives, we like to learn the rules of logarithms. We like to estimate, let me see the time. We like to estimate a large number. We like to explore the change of base of a logarithm and apply logarithms in growth and decay. Okay. So some rules of logarithm, we're asked to, let's see, let m and n be positive. Let m, n, and a be positive real numbers where a is not equal to 1, and let r be any real number. So then we have, the first one is the product rule for log. Right? We have the log base a of m times n. Let's do like this. So log base a of m times n equals log base a of m plus log base a of n, right? So the log of the product can be broken apart into the sum of the logs, right? The log of the product is going to be the same as the sum of the logs. Okay? So the logarithm of the product of two or more numbers is the sum of the logs of the numbers. Okay, so if we have the product rule, the next logical flow would be, oh, maybe there's what, a quotient rule. So then I'm just going to kind of go straight to it. So the log of the quotient is going to be the difference of the logs. Again, the log of the quotient is going to be the difference of the logs. And again, just stop me if anything is not clear or anything of that nature. We talked about the product rule, the quotient rule, and the last one that's not necessarily obvious is this thing called the power rule, right? So the log of a power is going to be the power times the log. The log of the power is going to be the power times the log, right? So when you take the log of a power, you can bring the exponent down in front and multiply with the power, right? These are equivalent. So you can kind of flow between these as necessary. You can start on the left and finish on the right, start on the right and finish on the left. Okay. So this example, it says, given that the log base 5 of z equals 3 and log base 5 of y equals 2, evaluate each expression. Let me see if I have, hopefully I have enough space here. So then for part A, we have log base 5 of y times c. Okay, so we just said what we had a, let me see the time. So as soon as I finish this one, I'll check attendance. Product rule, right? The log of the product is the same as the sum of the logs. So then this is going to be the same as log base 5 of y plus log base 5 of z, right? But then it says log base 5 of y is 2, log base 5 of z is 3, so then that one is 5. So then for part B, we have a couple of rules at play. I'm just going to kind of jump to them. Let me see. Let's do it like this. So we have the product rule in conjunction with the power rule, right? So the log of the product, we can rewrite it as, so part B is the same as log base 5 of 125 plus, I'm going to go ahead and apply the power rule as well. So if we had a log base 5 of y to the power of 7, that power can come down and you multiply it. It's going to be log base 5 of y, right? Let's see. Now 125, what is that? 5 to the power of 3. So I am kind of running out of space a little bit. So 125 is 5 times 5 times 5. So then that's going to be the same as 3 times log base 5 of 5 plus 7. Log base 5 of y is 2, right? Right here, log base 5 of 5, that's actually just 1. It's just 1, right? So 3 times 1 is 3 plus 14, that one is 17. I just put on. So let me go ahead and get a copy of these guys. Okay. So we have this log base 5 of the square root of z divided by y. Square root, let's go ahead and rewrite it as a power. I'm gonna show a few more steps here since I have more space. This is the same as log base 5 of z divided by y to the power of 1/2, right? So then we can first apply the power rule where this 1/2 comes down in front. So then this is going to be the same as 1/2 times the log base 5 of z divided by y. Then we can apply the quotient rule. So then that's going to be 1/2 times log base 5 of z minus log base 5 of y. Okay. We said, so that's 3 minus 2. So then this is going to be 1/2 times 3 minus 2, which is 1/2. Thing isn't clear, or if we need to go back. I'm about to check attendance. I just have one more part to do. And then for part D, so we have log base 5. We got this z, is that a typo? I think this one's okay. Z to the power of 1/30 times y to the power of 5. Okay. So we can apply the product rule first. This is going to be the same. I'm going to go ahead and apply the power rule as well. So then we can expand this into 1/30 times the log base 5 of z plus 5 times the log base 5 of y. So then this is going to be 1/30. Z is 3 plus 2. 1/10 plus 10 . Let me check this really quickly. Let's see how do we do. So we got 5, 17, 1/2, and 10.1. See the 5 here. 1/2. 17 and the 10.1. Okay. Check this again really quickly. Ooh. Okay. So let's keep going. So if you're just joining us, we're doing something a little bit different today. I did not make the lecture in advance. So instead of doing it in advance, I'm doing it live, right? Okay. Let's see. So in this example, we're asked, write each expression in expanded form, right? Okay, so I'm just going to kind of just apply the rules that we just discussed. So I'm going to write a little bit more shorthand. So the first one I would apply, I'm going to do the quotient rule, and actually I'm going to just kind of do them in one go. So for part A, let's see. So the first one is going to be what? 2 times the log base 2 of x plus 3 log base 2 of x minus 1. Okay. And then minus log base 2. We gotta do that 4. It's gonna be 4 times the log base 2 of 2x plus 1. All right. So basically, like right in here, right? Like in the top, we have multiplication as the main operation, and then we have division, right? So this multiplication, I turned into this plus that you see there. The power rule, that's where this 2 comes from. When you apply the power rule in this term, that 3 is right there. The quotient, you see it in the minus there. The 4 is right there. Again, that's a power rule again, right? So again, there's a product rule, quotient rule, and power rule. Okay. So this is expanded form. Clear. So if you're just joining this, but I think I said that already. That I didn't do the lecture in advance. I'm doing it now. And again, if anything is not clear, just stop me and we can talk about it. And then part B. So that square root is the same as to the power of 1/2. So then if I apply the power rule first, I would have 1/2 times. Then we can do the product rule and the power rule at the same time. So we're gonna have 3 times the log base c of x plus 2 times the log base c of y plus 5 log base c of z. Log base 2 of x, 3 log base 2 of that. I think we got all of this. Okay, so they distributed the 3. I mean, like I stopped at this line. They just want to distribute that 1/2 and they got this. So that's fine. Right expression. So now we saw several examples where we expanded these logs using the rules of logarithm. Now we're gonna work the opposite. We're gonna start in expanded form and see can we condense it, right? So the difference of 2 logs is the quotient. So this is gonna be the log. See the top, we're gonna have 3x over 4y. If we did the quotient rule in reverse, it should be log of 3x minus the log of 4y. Okay. So then with those constants that's on the outside of the logs, they become the exponents. But then this next one, and let me shrink this down. For that first part, we have 2 times the natural log of x, so that's going to become x squared. And then 1/2 of that next part is going to be the square root, and since we're doing plus, that means these are multiplied. So we're going to have the square root x squared plus 1, and we're taking the natural log of that. So the idea is that we're applying those rules of logarithm in reverse. Let me check it one more time, because if I started with that answer, that 2 would come down in front, it would be a plus, that 1/2 would come down in front, and yeah, I think that's it. Okay. So then the next one, let me see, looks like we have 5 squares, and then there's a 25. If it's plus, then it's going to be times 9 divided by 75. Because we can at least factor out a 5. It looks like a 15. I'm trying to use my space, but I'm running out of space. So I know I should give myself more space, but it's been a little bit, whatever. So if we factor out 15, right? So then this is going to be equal to, then let me see. So here, let's do it this way. So 25 is what? 5 times 5. 9 is 3 times 3, right? 75 is what? 25 times 3. So then that's 3 times 5 times 5, right? Notice this is all multiplication and division, so we can cancel like products. So then, for instance, this 3 cancels this one, this 5 cancels this one. So we're left, and this 5 cancels this, and so it boils down to 3. Now, I don't know if they wanted us to simplify it like that or not. It looks like it all boils down to log base 2 of 3. To me, this makes more sense instead of not doing this. I'll leave my work up on the side. And let me make those the same color so that way if you're looking at this later, those guys. Let's do right, this is what we got there. So we're going to leave that for right now, and we'll check it in just a moment to see how do we do. For this one, let's see. So we have all those pluses and minuses, so those change into multiplication and division. So on top, we're going to have x times x plus 1. On bottom, we're going to have x squared plus 1. It doesn't look like anything cancels. And then since we have times 1/3, that becomes the power. So we can, and to the power of 1/3 is the same as the cube root of all of that, right? So kind of went through that one a little bit quickly, and then we need to say what the natural log of all of that. Outside my window, there's a dog park. And I guess like as people coming in and out, they're opening that gate, and that gate sounds like the Matrix. It's like, yeah, it's that Matrix sound. It's like screeching metal almost. It just feels like the Matrix. It's so weird. And then it's like at this stage of my life, I've kind of like, I don't punch a clock anymore. Like the most clock punching I do is with you guys, like just trying to be available for you guys. But if I weren't for you all, I would not look at the clock at all. And so what happens is it feels like Groundhog's Day. Like, I don't know if you ever saw that movie. It's a really good movie if you just want something different to watch. It's older built. I think it's Bill Murray. But it was trippy. But it's trippy because like basically he wakes up and it's the same day. He keeps repeating the same day over and over and over. But like that's what it feels like to me. I was like, oh, this is weird. So then I started pondering like, well, what is time? It's a man-made construct. What if who said that like, you know, this is Monday and Wednesday and we have work days and weekdays and my mind would be like going all over the place. It'd be so interesting. And but it's real trippy. Okay, let's see how do we do. Let's see the time and I'll check the Zoom in just a moment. Okay. As we just said, this whole man-made construct of time. All right, so then we got this log of 3x divided by 4y. Okay, cool, we got that one. Natural log x squared times the square root of x squared plus 1. Natural log x squared, okay, we got that one. I feel good about these. Yeah, cool, we got the log base 2 of 3 and the cube root. All right, we got okay, so another reason I didn't mind like doing the condensed steps because I knew I had like a typed up version of all the necessary steps. And again, if anything is not clear, or if you want to ask me any questions, just stop me and get my attention and we can talk about it. Let's see, let me pause right here for a moment to check in on Zoom. Okay. If we go to the chat, no worries. If you are here, you are good to go, right? Okay. So digits and common logs. So now I did, like I said, usually I don't look at these like in great detail in advance, but I was kind of scanning through and I was like, wait a minute, I don't think I've seen this before, right? So I guess this is like one application of like logs. And let's just see what happens, right? So it says digits and common logs. A positive number k has n plus 1 digits if and only if the log of k is an interval n to n plus 1, right? So the log. So this is just like a corollary or something. So it says a positive number k. So this is telling us how many digits this number k has, if and only if the log of k is in this interval. Okay, so let's see. So then it says write an estimate of this number in scientific notation. So scientific notation, usually you have like some number between one and between 1 and 10, right? Times 10 to some power, right? And it's usually an approximation. So for instance, so we want to get this to like a base 10, right? Let's see. So if we start, we have this k equals e to the power of 700, right? We just said that k has n plus 1 digits if and only if the log of k is between n and n plus 1, right? So let's look at the log of k and see where it goes. So if we take the log of both sides, let's do it like this. This guy and the log of this guy, we can apply the power rule, right? The log of a power is going to be the same as the power times the log. Right? So then if we bring down our equal sign on the left, we're going to have the log of k, right? We're going to have 700 times the log of e, okay? That number. So we have 700. Okay. So in order to do that, all right, reload and refresh. Cool beans, okay. Time. Let me see. 700 times the log of E, 1. So then, I don't know why I did that. I'm going to say this is approximately 0.0061373, right? So then, so this tells us that what? That original thing is going to have 304 point whatever is between 304 and 305. So what this means is that the original number should have approximate or should have like 305 digits. All right. So then if we want to go back to get an estimate for K, oh, I'm almost out of space. So this log, this is common log base 10. All right. So we can rewrite this as an exponential. All right. This is the log form. Now we're going to go back by writing in the exponential form. So then this is going to be, and basically we do that by swinging the base, and now it becomes the base of the exponent. So then we're going to have K is going to be approximately 10 to the power of 304, blah, blah. Okay, let me think about it. Or, okay. Let me add some space. So then, and I see the time, I'm about to let you guys go. So then this part, I'm just going to kind of continue here. It's going to be the same as 10 to the power of 0.0061373 times 10, let me think about it, or of 304, right? The part we need to, let me do that in the calculator real quick and see what happens. So if we said, actually, can I pull back up what I had? I want to remove that 304. Okay. I want to say 10 to the power of that answer, and we get this, right? Okay. There's one thing off that I'm not sure about. 1.01, 1.01423. Okay. I'm just gonna say 1.01423. I think this is supposed to be 305, but I don't know why. There's something that I'm missing somewhere. And I think the theorem, the corollary or whatever that was, says a positive number has n plus 1 digits if and only if this is between n and n plus 1. So our log of k was between 304 and 305. So we need to have 305 digits and not 304, right? That's just a direct application of what they were saying. And 1 to the power. Let's see, how do we do? This is what we got. Let's see if it's correct. We're gonna go back and go through it one more time just to clean some stuff up. Matter of fact, let me get all this on that one slide. This concept I had never seen before. I was like, oh, but it's just an application of things that we have been talking about. So it's like once you at least have the foundation of what we're speaking on, then you can apply it to like different stuff, right? And that's what you just witnessed. Like I said, I hadn't seen that. So we got this 1.01423, and again, I just truncated it to the power times 10 to the power of 305. Okay, let's see. Okay, that's correct. I don't know why I felt like I needed 305. Since this is between the integers 304 and 305, the number k requires 305 digits, right? So then the 10 to the 304 gives you 3 or 4 digits, and then the first part gives you the additional digit. Okay, so I just second guess myself. So that was a lesson learned, right? Don't second guess yourself, right? As much as we might be tempted to do it, let's copy. I didn't mean to copy that. That's fine. Okay. Let me see. We're not done, but I didn't really want to keep you all longer. Now, again, like I said, when I open, if I don't finish by the end of class, I'm going to release you guys, and I'm just going to keep going, right? So, if you're welcome to leave at this point, but I'm going to go ahead and at least finish out this section. Okay, guys? Let's see. And then if you are leaving, we'll meet back same place, same time on Friday. This is what, section 3.3, rules of logarithm. We have one more section in this chapter. This is what, the top of week 6. I think our exam 2 is scheduled for week 8. And then after that exam 2, I think we move into spring break. Okay. So take care, and I'll see you guys on Friday. And I'm going to go ahead and finish this out. I still got about 16 more slides to go. Okay. All right. So yeah, we were fine. I don't know why I second guessed myself. Okay. So now change your base formula, right? Change your base. Let's see. So let A, B, and X be positive real numbers where A is not 1 and B is not 1. Then the log base B of X can be converted to different bases as follows. So if we have log base B of X, we can rewrite that as log base A of X divided by log base A of B, right? So say we wanted to change the base to base A, you can do it in this fashion. But this is going to be the same as a log of X divided by log of B. So that base is base 10. So basically, we took that base B and basically divided by the log of that base, right? And then, all of these different expressions are equivalent. Okay, so that's the change of base formula. You may have seen me use that before, right? Sometimes I just default to it, like especially when I'm crunching things in the calculator. When I have like different bases and I still want to see the number, so then I use this change of base formula. So then we're asked to compute the log base 5 of 13 by changing to a common log and natural log. Thank you. So I think they're the same in either case. You can say log base 10 of 13 divided by log base 10 of 5. Again, we just said the log of this divided by the log of the base, and we'll get this result. And then if you did natural log of this divided by the log of the base, equation of the form y equals c plus b log of x base a, whose graph contains this. So we got a log function, okay, and it contains these points. Okay, so let's plug these points in. I feel like I'm going to need some space, but for right now, I'm just going to go with it. So it's 2, y is 3. Let's plug those in. So then we're going to have, and I'm going to put my y on the right hand side. So we don't know what c is just yet. So we have c plus b log base a of, now for the first one, x is 2, y is 3, okay. The points for the second one, c plus b log base a, when x is 4, y is -5, right? So let's solve for c from the first one and then take that and plug it into the second one. So if we solve for c in the first one, we're going to get what? C log base a of 2, right? Now let's take this and plug it into the second equation and see what happens. So then if we take this, we're going to have 3 minus b log base a of 2 plus b log base a of 4 equals -5, okay? Three from both sides. So I'm going to say plus a -3 here, plus a -3 here. And then I'm going to condense that log down. I'm going to basically switch these orders, but I'm going to apply the reverse. Okay. So those are the changes that I'm doing. So then if we account for those changes, right? So if we have that, the log of 4 minus the log of 2, let me think about it. So 4 b divided by, and we're going to have the log base a of that, and that's going to equal, looks like -8. Okay, almost there. I'm going to kind of just work over here to the side. So now we can rewrite this log as an exponential. If we swing the base over and make a few other adjustments. Okay, so I'm going to rewrite the log as an exponential. This is going to be the same. Let's say 4 divided by 2. That's going to be b equals a to the power of -8. Right? These are equal. So this implies what? A equals 2 and b equals -8. Okay. So if we put, oh, and then we can use this to go back and solve for c. Wait, let me see. Okay. I'm going to add a page, and then I'm going to shrink out D and get it back on one page, right? So we got A, we got B. So then earlier we said that was C. Where is it? So I'm going to take these and solve for C, right? So then we can say C equals 3 minus B, which was -8. So that's going to become +8 times the log base 2 of 2, okay? So log base 2 of 2 is 1. It's almost like if you use the change of base, they essentially cancel it out. So this guy collapses to 1, okay? Three plus 8 is what, 11. So then long story short, we can check, we're gonna check this. Y equals our C, we got 11. Our B, so it's gonna be a minus 11 minus 8 log base 2 of x, okay. I wanna get, this is what I had earlier. Sorry, I know I'm going way back. And we'll check to see how do we do. Let me just shrink this down. Leave it expanded. That page, I'll just leave it here. The result that we got. Oh, and then we want to check. These numbers work out. Okay. So let's see. So let's put this in, let's go to our y equals, and we'll type 11 minus 8 log of x. So to capture that change of base, we're going to say log of x divided by the log of 2. That'll capture the change of base, right? So I'm going to quit, and then I'm going to basically plug in these different x values and confirm I get those y values. So I go to variables, y variables, number 1 function, number 1. So 2, we should get 3. And we'll just recall, and then when x is 4, we should get -5. You're able to check that. So we got 11 minus 8 log base 2 of x. Let's kind of walk through what the text did. So first they plugged in the 2 points, right? And so you can see equation 9 and equation 10. And then they subtracted one from the other. Okay, I think I did mine a little differently. I solved for C, and then I took that C and plugged it in, but this is the same thing. So I use the substitution method, they use the elimination method, right? I think we'll talk about that here. I think about different ways of solving a system of equations, right? So they were able to get B when they did theirs, and that makes sense because the C's cancel out. You saw 2 different ways, but we got to the same conclusion, right? So, so basically, the destination is fine, but, what's more important is the journey. How did you get there, all right? Okay, but we got the same thing. So then we have this half-life formula. So it says the half-life of any quantity whose value decreases with time is the time required for the quantity to decay to half of its initial value. The half-life of a substance undergoing exponential decay at a rate k, where k is strictly less than 0, is given by this formula. H equals the negative natural log of 2 divided by k. So the way I remember this, I usually call it, you might hear me say kt equals negative natural log of 2, because we're doing half-life. If it was doubling time, it was kt equals the natural log of 2. Basically, you just remove the negative. Where k is your rate and the t is the time. Right? So that's how you usually hear me say it. That's how I remember it. Whenever it's either half-life, if it's half-life, there's a negative. If it's doubling time or tripling, whatever, it's going to be positive. And then I just say kt equals the natural log of 2. And then, just introduce your positive or negative as necessary. Well, I usually suppress the word beforehand, but I didn't hear. It says in an experiment, 18 grams of radioactive element. I guess I could go ahead and do it. Just work this one. So let me, I'm going to get a copy. I know we can see the solution, but I'm going to get a copy. So then look at that. Right now, we're just going to drop it right here. Let's add a page right here. Exponential growth model. So with this one, the way I can see a lot of this, I have to work it myself. In an experiment, 18 grams of the radioactive element sodium-24 decayed to 6 grams in 24 hours. Find the half-life to the nearest hour. Now they went through all the back. I guess we can start there. I was going to start with the half-life formula, but we can start with the exponential decay formula. So that's like PERT. Let me see. So we're going to do it like this. A of t equals A naught times e to the negative kt, right? This is just exponential decay formula, right? So it says in an experiment, 18 grams of the element sodium-24 decayed to 6 grams. Okay. So let me back up. Okay. So amount, we started with 18 grams, all right? We finished with um, the finishing amount was finished with, so it's half of it, 6 grams, right? It was 24 hours. Okay, 5 to the nearest hour. Okay. So in order to find the half-life, we need the rate, right? Okay. So, and if we wanted to do a direct, for instance, suppose we want to do a direct application. Now, again, the way I remember half-life, I remember this KT equals the negative natural log of 2. If it took, to me, I'm like, why not just go ahead and put, okay, we're going to come back to the purple part. Let's use the blue part for right now, because I know that's what the intent is. So they gave us the starting amount, they gave us the finishing amount, and then they gave us the time. So I think the only piece of information that we don't know is the rate, which is our K. So let's plug these different parts in and see, can we solve for K? Okay. We have 6 equals 18 times E to the negative, we don't know K, and the T is 24. So 20, we're gonna write it as 24K. Right? So then if we solve for K, divide both sides by 18. So we get 1/3 equals E to the negative 24K. And then if we want to get that out of the exponent, we take the natural log on both sides. The front, and these are going to cancel each other out. So 1/3 is the same as 3 to the power of -1. So we can write that as negative natural log of 3 equals negative 24K. Divide both sides by half. That's why we couldn't jump straight to it. Yeah, that's fine. Yeah. I was like, why can't we? Because that wasn't the half. That wasn't the half, right? Because I was trying to jump straight into the half-life formula, and I was like, why can't I? And I realize now why I couldn't, because 6 is not half of 18. If they had told us it took 24 hours to go from 18 to 9, then we can use a half. We can just jump straight there. But we didn't. They didn't give us that off immediately. Okay. So then we're using this to find the rate, and then we can solve for the half. Long story short, K equals 3 divided by 24. Well, yeah, that's not the final answer, but that is a part that we need. And that, okay. And I'm gonna leave it like this to just keep it exact as I work, because again, we don't want to truncate any numbers until we get to the very end. If we start cutting the numbers before we get to the end, it's going to throw up the final answer. So now we have our K. So then for the half-life, now we can use the half-life formula. If we take this K and plug it in, that'll tell us the half-life, how long it takes for half of that to remain. So then again, we're working with like KT equals the negative natural log of 2. So then our half-life is going to be equal to T. In our case, we called it T. And that's going to be the negative natural log of 2 divided by K. So then in this case, it's going to be log of 2 divided by, I'm basically divided by a fraction, so I'm doing key change flip. Right here. So we're dividing by the natural log of 3 over 24, right? So now we can crunch that number to get the half-life. Like this, negative 24 times the natural log of 2 divided by and that's going to give us the hours, right? So then negative 24 times the natural log of 2 divided by the natural log of 3. Maybe we didn't need the negative. It's about 15 hours. So that's about 15 hours. Maybe I didn't need the negative. Put things off. Copy. Okay. So you see, this is like PERT, right? The starting amount, the finishing amount, the rate, and the time. And I think we got all of this. We got this. We got this. We got this. Let's keep going. Okay, so I just missed the negative. So wow, we actually wrote the right thing, but we didn't understand why, right? Like right here, because we got the negative there, and then because K is not negative, we did their 1/3. I must, oh, I had the wrong formula somewhere. Okay, so, oh, okay, my headphones. Just a moment. Nope, no cancel. Okay. Okay, that's better. Which else? Okay. So the only thing was I should have just used exponential growth right here. Let me get rid of this guy. I knew I had a negative off somewhere. So I'm gonna get rid of this. Okay. So that means that this negative is gone. This negative is gone. This negative is gone, and this has a negative, right? Okay. So then, if my K has a negative, now that means this negative is gone. This negative is gone. Okay. I knew something was off, and it's fine. I was trying to use the exponential decay model, and I should have just used exponential growth and go from there. That's fine. Okay. That's fine. We're almost there. We got to the bottom of the missing negative. Okay, and we got approximately 15 hours, right? We got the same result. Okay, radiocarbon dating. So carbon-14 is a form of carbon that decays radioactively with a half-life, time required for half of any given mass of decay of 5,700 years. After the organism dies, the age of its remains can be calculated by determining how much carbon-14 has decayed. Okay. So in 1960, a group of specialists from the British Museum investigated whether a piece of art containing organic material found in Tutankhamun's tomb had been made during his reign or whether it belonged to an earlier period. We know that King Tut died in 1346 BC and ruled Egypt for 10 years. What percent of the amount of carbon-14 originally contained in the object should be present in 1960 if the object was made during Tutankhamun's reign? That's the best I'm going to be able to say on King Tut's name. The half-life of carbon-14 is approximately this. Okay, let me see here. What's the question actually? Okay, so to give us the time, let me see. Okay, so the half-life of carbon-14 is approximately 5,700 years, right? So then if we're using the exponential growth, if we start with this amount, here's the time, we should finish with half of the starting amount, right? So then you can solve for K from here and you get this result. Okay, and then you have this. So the question, let me see, it says, what percent of the amount of carbon-14 originally contained in the object should be present? What percent? Okay. Let's keep going. So let X represent the percent of the original amount in the object that remains after T years. So X is the whatever is the percentage left, right? So X percent of the original. So then X equals this guy, you would crunch that number in the calculator. Okay, 3,300 years. So the percent X of the original amount of carbon-14 after 3,306 years is about 67%. And again, I just crunched it. It says the time elapsed between King Tut's death from, it was 3,306 years, right? I think they gave that in the passage. So we had a time, we plug it in. That was interesting. Okay, yeah, I don't know. Anyway, I usually suppress it. I realized I hadn't, but it's been a long time, so I'm gonna go with it for now. So it says King Tut ruled Egypt for 10 years. It says the time that elapsed from the beginning of his reign in 1960 is 10 years. So the percent of the original amount of carbon-14 remaining after 3,316 years is going to be about 67%. Thus, if the piece of art was made during King Tut's reign, the amount of carbon-14 will be about 67% remaining. Okay. So, you know, so we'll get some more practice. We have homework assigned for these concepts to get some practice. So, you know, we have to do the best that we can. Yeah, okay. On that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. All right, take care. Peace.